Good morning, good afternoon, or good evening, all. A very warm welcome to you. I'm delighted to have Professor Shao from McGill University with us today. Dr. Shao is an assistant professor at McGill. Prior to joining McGill, he worked as a postdoctoral scholar at the University of California, Berkeley. Before that, he received his master's and PhD from Stanford University in structural engineering and his bachelor's from Yunnan University. His current research focuses on sustainable infrastructure through the development and application of high-performance materials, optimization tools, and autonomous construction methods. He has over 10 years of research experience in structural concrete and advanced cementitious materials, with emphasis on UHPC. And he's an active member of ACI 239C UHPC structural design. So thank you, Dr. Shao. The talk is titled Structural Design of UHPC, Challenges, Methods, and Opportunity. It's all yours.
All right, thank you, Prannoy, for your introduction. And it's great to meet the colleagues and students from University of Miami and probably from rest of the world as well. So today I'm very honored and humbled to share some of my thoughts on the structural design of ultra high performance concrete, or we usually refer to UHPC. So the entire scope of the structural design is very big. So I hope my talk can start the discussion and draw your interest to this wonderful material. And of course, if you have any questions, comments, you're welcome to ask and share at the end of this talk. So this talk will be divided into two parts. The first part will talk about the UHPC structural design theory. I will briefly introduce the material design and behavior of UHPC, since some of you may have a lot of knowledge of UHPC and the rest may heard about the material for the first few times. And then we'll discuss the flexural behavior of reinforced UHPC beams, as well as the prediction methods of reinforced UHPC flexural behavior. And then we'll talk about the UHPC beam design philosophy according to structural analysis, carbon foot analysis, and corrosion analysis to discuss how we may best utilize this wonderful material. So let's get started. So what's a material what is UHPC? So basically UHPC is very similar to conventional concrete. It has aggregates, it has binders, it has waters and chemical admixtures. So there are three key differences between UHPC material design and traditional concrete material design. First is UHPC typically does not include coarse aggregates, although there are some recent research trying to reintroduce coarse aggregates, but most of the UHPC materials does not have coarse aggregates in order to avoid the weak interface or transition zone between the coarse aggregates and the matrix. So that's the first key difference. And the second is for UHPC, in order to minimize the porosity in this material, people adopt this, what they call as packing density theory, in order to fill the gaps between larger particles with medium particles, medium gaps with smaller particles, to the very fine degree that people are even trying to fill the gaps between cement particles by silica film. So that's the second biggest difference between UHPC and traditional concretes. People are trying to use packing density theory to really minimize the porosity. And third biggest difference is people are using a very low water to binder ratio in UHPC in order to minimize hydrated water and the resulting pores in order to minimize the porosity as well. So those are the three key differences between UHPC material design, traditional concrete material design. And then also in UHPC material, people typically add short discontinuous fibers, typically steel fibers with a fiber volume of around 2%. That's typical in current engineering applications. And these short fibers will bring very high material toughness or material ductility in UHPC material. So after briefly talking about the material design of UHPC, let's talk about the material level mechanical behavior of UHPC and how it's compared to conventional concrete. So here the green line represents UHPC and the blue dashed line represents conventional concrete. So under tension, traditional concrete will behave linear elastically until cracking, and after cracking, it will lose its tensile strength very quickly because there's nothing bridging the cracking plane. In contrast, for UHPC, after cracking, which is at a higher strength level than traditional concrete, it will show us what we call a strong hardening branch. And during this strong hardening branch, fibers are bridging the cracks and then cause what we call as multiple cracking phenomenon. So UHPC material will show multiple fine cracking with increasing tensile strength after cracking point until the material reaches a point what we call as crack localization. So at crack localization point, one cracking plane will start to localize and the UHPC tensile strength will start decreasing. And after crack localization, all the deformation will be concentrated in the single localized crack instead of spread along the entire specimen. That's about the material tensile behavior of UHPC. In terms of the compression behavior, UHPC will have a compressive strength like typically between 130 and 200 megapascal. That's about 3 to 5 times the compressive strength of traditional concrete, as well as UHPC show high compressive toughness because the fibers are bridging the spalling cracks and enhancing the post-peak compression toughness of UHPC as well. So that's about the UHPC material mechanical behavior. It shows tensile strength hardening with until crack localization and show high compressive strength as well as high compression toughness. And also because of the dense microstructure of UHPC due to the minimized porosity, as well as the superior cracking control due to the fiber bridging, UHPC are usually expected to show very high corrosion resistance compared to conventional concrete structure. And therefore, UHPC has gained increasing attention and applications in both the research world and as well as real-world applications. So across the world, UHPC has been increasingly applied into different infrastructure projects. So now we know that UHPC shows superior material performance. But since structural members are always reinforced by reinforcing bars, we are wondering if these superior material performance will lead to superior structural performance. And that's the belief of the community decades ago. But the question is this really true? Can superior structural performance really always lead to superior structural behavior? So in the next discussions, we'll always refer to the material behavior of UHPC we just briefly reviewed, and then think about how it will change the traditional reinforced concrete flexural behavior that we have been believed so far or have learned so far, which includes a cracking point, yielding, and crushing point of reinforced concrete behavior. So we'll talk about how the unique UHPC material behavior may alter the classical flexural behavior of reinforced concrete. So before our discussion, let's look at the load deflection curve of one typical reinforced UHPC beam and typical reinforced traditional concrete beam. So these beams are singly reinforced beams with tension reinforcing steel at the bottom and it's simply supported. And these two beams are identical in terms of the geometry, loading condition, boundary condition, as well as the reinforcing ratio. The only difference between these two beams are one beam is reinforced by UHPC with 2% fiber volume, another is reinforced by traditional, one beam has a matrix as UHPC, other beam has matrix as conventional concrete. So these two beams have the same reinforcing steel and same reinforcing ratio. So compared to reinforced concrete, reinforced UHPC show higher load capacity as expected because we show higher tensile strength as well as higher compressive strength. But what's surprising is reinforced UHPC may actually show early failure than reinforced concrete beam. And this is very surprising because if we go back to here, UHPC shows higher material ductility than our conventional concrete. So the question is, why like on the structural level, reinforced UHPC may show lower ductility than reinforced concrete. And how can we design reinforced UHPC members to actually show superior structural level performance as well? So that's this, like addressing this question will be the focus of the first half of this talk. And then to understand the flexural behavior of reinforced UHPC, we need to understand the flexural tension behavior of steel reinforced concrete. So we need to understand the tension behavior on the tension side for the steel rebar combined with UHPC. And in order to understand the flexural tension behavior of rebar reinforced UHPC, we need to understand the bond between steel rebar and UHPC. So we'll start from the reverse order, first talking about the bond, then talking about the flexural tension, and then talk about the flexural behavior of reinforced UHPC beams. So first, let's look at the bond failure mechanism of cementitious matrix system. So if we are pulling a rebar out of concrete, then we know that the hoop tensile stress will form around the steel rebar, and then it will form splitting cracks along the steel rebar. And for UHPC, because of the fiber bridging, those fiber bridging will very well restrain the opening and the expansion of splitting crack. So it will provide very high splitting resistance. And when high splitting resistance is provided, then the splitting failure will be transformed to a proud failure, which means the UHPC keys between the steel rebar ribs will be sheared and crushing. And when the proud failure is happening, then the high compressive strength or the dense matrix will increase the mechanical anchorage between the steel rebar and the UHPC matrix. So because of the high splitting resistance from fiber bridging and high mechanical anchorage from the high compressive strength, if we look at the bond stress versus bond slip curve, we'll find out that UHPC shows much higher bond strength as well as bond toughness when compared to conventional concrete. So UHPC shows very superior bonding with steel rebar. And then what will happen is if we are looking at the flexural tension behavior of steel rebar reinforced cementitious matrix. So we are showing a direct tension test of a cementitious matrix with steel rebar in the middle. And we can find out that for traditional reinforced concrete, if we are looking at the what we call tension stiffening behavior of the reinforced concrete, the concrete will show multiple multiple large cracks as well as very significant splitting cracks along the concrete. And then this will allow us to utilize the high tensile strength capacity of steel rebar, and the reinforced concrete tension stiffening specimen can show a large deformation capacity. On the other hand, for reinforced UHPC under direct tension, so it has a steel rebar in the middle. For reinforced UHPC on direct tension, first, it may show a few localized cracks. But what's more important is after the formation of localized crack, if we are looking at the strain gauge reading near this localized crack, the splitting cracks are very well restrained. So the steel plasticity is restrained within a very small region near the localized crack. So this is very important that the high bonding of UHPC are actually restraining the steel plasticity within a very small region near those localized cracks. So before we talk about the UHPC shows higher tensile strength capacity than conventional concrete. But if we are comparing the tensile strength capacity of UHPC in this black line compared to steel rebar, so we normalize the tensile stress to have a more clear comparison of the tensile strength capacity. UHPC shows the tensile strength capacity of UHPC is still much lower than the tensile strength capacity of steel rebar. So in order to achieve high tensile strength capacity of reinforced UHPC, not UHPC itself, but steel rebar reinforced UHPC, we need to utilize a high tensile strength capacity of steel rebar. So at the ultimate stage, we want the steel rebar to show to better utilize high plasticity in steel rebar in order to get the high tensile strength capacity of the rebar reinforced UHPC, the composite behavior. Now, after understanding the high bond as well as the plasticity concentration near the localized crack, we can try to look at the flexural behavior of reinforced UHPC beams. So here we are comparing the load and mid-span deflection curve of two UHPC beams. And these two UHPC beams have the same fiber volume, 2%. The only difference is the reinforcing ratio. So the green line represents a beam with high reinforcing ratio, while the orange line represents a beam with a low reinforcing ratio. So you can see there, for the orange line, the beam with low reinforcing ratio, UHPC show a linear elastic behavior. After cracking, the stiffness reduced until we reach a point what we call as crack localization, which means the one localized crack has starting forming in the weakest plane of the beam. And because of this beam has a low reinforcing ratio, so the strong hardening of steel rebar. So what we see here after yield and crack localization, the strong hardening, the post-yield strong hardening of steel rebar cannot compensate for the fiber bridging loss in this beam with a low reinforcing ratio because we have little amount of steel rebar, and then the strong hardening of rebar cannot compensate for the fiber bridging loss after crack localization. And therefore, the flexural stress start decreasing after the cracks localize in the weakest plane. So we cannot open additional localized crack because the flexural stress is decreasing. And then the plasticity concentration cause the steel plasticity to be restrained within a very small region near the localized crack, and we have early rebar fracture here. On the other hand, for this green line with a high reinforcing ratio, because we have a higher amount of steel rebar, then for this beam, the steel stress hardening capacity of steel rebar compensates for the fiber bridging loss or the flexural tension capacity reduced due to the fiber bridging failure after crack localization, and the beam gain an increased flexural load capacity. And because the flexural stress increased after cracks localized in the weakest plane, additional localized crack can form, which help spread the steel plasticity from one single location to multiple locations, and therefore we can delay the steel fracture here. And also, steel rebar can hardening in UHPC beams because of the high crushing resistance of the material. For traditional reinforced concrete, we typically cannot utilize the post-yield hardening capacity, but for UHPC beams, we can because of the high crushing resistance of the beam. And here we are showing the constant moment region of this beam at the peak load. So the photo are showing the constant moment region of the two beams we just discussed at peak load. So for the beam with low reinforcing ratio from the DIC system, we see that the UHPC material is still linear elastic in compression. So it has not actually reached its full compressive strength yet. At this point, the steel rebar just yield, and then the maximum crack width is very small, which means at the peak load, the fiber bridging starts failing. So fiber bridging failure causes the load capacity reduction here. Well, for the other beam with a high reinforcing ratio, the DIC reading shows that the UHPC material is softening in compression with a relatively large compressive strength, and the steel strength gauge readings shows that the steel rebar has significantly hardened. We are utilizing the post-yield hardening capacity of steel rebar, and the crack width, the large opening crack, has indicated that fiber bridging is almost lost here. So the flexural tension capacity is taken over by the steel rebar in place of fiber bridging. And then so here we show the like strength distribution of these two bars of these two beams at the peak load, we can show that by increasing the reinforcing ratio, we are changing the failure mechanism from like a crack localization or fiber bridging failure cause failure to crushing cause failure, which is similar to our typical reinforced concrete beams. And by increasing the reinforcing ratio, we're increasing the sectional curvature at the peak load. So to summarize, we can observe that there are two different flexural failure paths for reinforced UHPC beams. So before cracking, we have both concrete compression force, steel tension force, and UHPC tension force. And after cracking, the UHPC tension force is still here because the fiber bridging is like providing the tension force according cracks until we reach a point at crack localization, which is typically very close to the yielding point of steel rebar. And after crack localization, the UHPC tension force carried by the fiber will start decreasing if the steel rebar hardening capacity cannot compensate for this tension capacity loss of UHPC, then the entire load capacity will decrease in the beam. And because the flexural stress decreased after cracks localized in the weakest plane, we can only form a single localized crack, and strong bond will cause plasticity concentration and early fracture. On the other hand, if we have a lot of steel rebar or the steel rebar is strong enough to compensate for the fiber bridging loss, although we may only have steel rebar tension force at the end, it's larger than the steel rebar yielding force plus the UHPC tension force at the crack localization point. We can have higher load capacity, and because the flexural stress increased after cracks localized in the weakest plane, we can form multiple localized crack. We can force other crack plans to localize as well and spread the steel plasticity into multiple locations and delay the steel fracture. And very importantly, the high crushing resistance of UHPC allows the steel to show significant hardening after yielding. And then, so we term these two failure paths as failure after crack localization or failure after crushing. And then to predict like which failure path UHPC will follow, we propose a ratio called omega, which is a ratio of steel post-yield strong hardening capacity and the UHPC tensile capacity. So it's relevant to the steel ultimate strength minus the steel yield strength, which is a post-yielding hardening strength of our steel rebar. It's relevant to the reinforcing ratio and relevant to the UHPC tensile strength at the bottom. Here, we are showing the drift capacity, which is a mid-span deflection divided by the shear span length, or like compared against omega ratio. So as we can see here, when the omega is very small, the beams are expected to fail rapidly after crack localization. So beam will have a small deformation capacity, which is here. And when the omega ratio is increasing, which means the steel post-yield hardening capacity is stronger and can delay the load reduction and can gradually increase the deformation capacity of UHPC beams until when omega is larger than 1, then we have failure after crushing, which shows much higher deformation capacity than failure after crack localization. So this trend is very well observed from the experimental tests of many reinforced UHPC beams. And because at low deformation capacity, omega shows a positive correlation with the deformation capacity. So in order to guarantee a minimum deformation capacity, we can actually set a lower limit to omega. So everything is to the right of this green line, and we can promote a high deformation capacity in reinforced UHPC beams. And by rearrange the omega equation, we can get the minimum reinforcing ratio equation for UHPC beams to guarantee a minimum deformation capacity to avoid rapid failure after crack localization. And then, for the flexural strength prediction of UHPC, Then we know there are two different failure paths. So we can first utilize omega to predict which failure path it will have. So based on the beam geometry and the material properties, we can predict the omega ratio to be larger or smaller than 1. If omega is smaller than 1, we know the beam is most likely to fail after crack localization. So the failure is mostly being triggered by UHPC crack localization on the tension side. So we should not use a crushing at the top. We should use UHPC localization at the bottom. For example, we may use a localization strength of 0.2 or determined by the material characterization test. And similar to steel reinforced concrete design, we have unknown variable C as a compressive zone depth. And then we can try to set up the force equilibrium where tension force equals to compression force. So a few things to note is we need to consider the UHPC tension force on the tension zone, and UHPC in the compression side may not reach its full compressive strength, so it may be in the linear elastic region. So we should not use a full compressive strength here. And then, based on the first equilibrium, we can solve for the unknown variable C and calculate the moment and curvature. And then if omega is larger than 1, we know that the UHPC, the crack localization stress loss can likely be compensated by steel strong hardening, so the beam will fail after crushing. And then similar to steel reinforced concrete beam design, we know that we need to use the limit strength as a crushing strength at the top, but instead we may use a larger compressive strength because of the high compression toughness of UHPC. And again, the unknown variable is still the C compressive zone depth, and then we can set up the force equilibrium. And then different from here, for UHPC in the compression zone, we know that it has reaches full compressive strength, so we can utilize the full compressive strength. And then the widely localized crack means that the fiber bridging is almost lost in the flexural tension zone. So we most likely can neglect the fiber bridging, although there may still be a small amount of fiber bridging near the neutral axis, but we may neglect them for simplicity. And then very importantly, we need to consider the post-yield hardening strength of our steel rebar, because the steel has hardened to take over the tension force. So we need to consider not only the yielding strength, but also the post-yield hardening strength of steel rebar. And similarly, after formulating the force equilibrium, we can solve for the compressive zone depth, and we can calculate the moment and the curvature. And to summarize that, we know that UHPC has high tensile strength, high tensile ductility, high compressive strength, high compressive ductility, high bond strength, and high bond ductility. And then those three material behavior are significantly altering the failure mechanism of UHPC. The high tensile capacity and high tensile ductility makes the beam prone to failure after crack localization, and the high bond capacity will cause steel plastic concentration and probably early fracture of the steel rebar. And then the high compressive strength and high compression ductility allow us to utilize the post-yield hardening capacity of steel rebar to potentially have a failure after crushing, and has a very high structural level ductility in the steel reinforced UHPC beams. And then we can further emphasize how we can utilize the unique material design of UHPC for flexural design. So we start from the fiber bridging provided by the steel fibers, as well as the minimized porosity provided by the packing density theory, minimized water to cement ratio, and as well as absence of coarse aggregates. So we can see there, so the minimized porosity will significantly reduce the permeability in UHPC and enhance the durability. The minimized porosity will increase the compressive strength of UHPC to enhance the cracking strength of UHPC, as well as anchorage and bond of fibers. the minimized porosity will help increase the elastic modulus of UHPC, it will increase the shear key strength and increase the bond strength of UHPC. As well as the fiber bridging will arrest the spalling and increase the compressive ductility of UHPC. It will bridge the tensile crack and bring high tensile ductility. It will bridge the bond splitting crack and bring high bond ductility as well. And from those material behaviors, we can think about how we may best utilize the material behavior for reinforced UHPC beam design. For example, to utilize high durability, we can reduce the cover thickness. Utilizing the high compressive strength and high compressive ductility, we can allow a higher reinforcing ratio than traditional steel reinforced concrete, because we know that the upper reinforcing ratio in steel reinforced concrete is limited by the concrete crushing. So with a high compressive strength and compressive ductility, we can utilize a higher reinforcing ratio in UHPC beams. We can utilize the post-yield hardening strength of steel rebar in the ultimate state. We can also increase the deformation capacity with a high compression toughness. And a high tensile strength and high tensile ductility can increase the cracking resistance at surface level, which is very important for the durability. We can increase the flexural stiffness, which is important because the structures are most often controlled by the stiffness. And the high elastic modulus can also help increase the flexural stiffness. And the higher bond can allow us to adopt larger diameter bars, which can be useful to increase the bar spacing, especially in congested steel rebar cage, to reduce the steel rebar congestion issue. So that's how we may use the unique material design and the resulting material behavior to enhance the UHPC reinforced UHPC flexural design. And then we'll move to the second half of our talk is about UHPC beam design. So a few motivations of the second part is, first of all, UHPC, because of the absence of coarse aggregates, has a much higher binder content and therefore carbon footprint when compared to conventional concrete. So the dashed line here represent conventional concrete, and many researchers has been proposing to replace cement by supplementary cementitious material, as well as reduce fiber content, because fibers actually represent almost half of the carbon footprint of our UHPC. And then, so we want to analyze and know what's the carbon footprint or the environmental impact of adopting UHPC in a structure, and then how will these two techniques affect the structural behavior as well as the durability as well as the environmental impact? So 2 questions: can we safely reduce the fiber volume to reduce fiber volume related carbon footprint? And then what's the implication of replacing cement with supplementary cementitious material? A second motivation is, compared to conventional steel reinforced concrete beam, many researchers has been proposing different design philosophies for UHPC beams. For example, some researchers have proposed that because of UHPC has such strong tension capacity, we can heavily reduce the tension steel area in steel reinforced UHPC beams to utilize the high tension capacity of UHPC, so we can have a very low reinforcing ratio and easy rebar placement. And other researchers may argue that we should use a similar reinforcing ratio as traditional concrete beam, but reduce the cross-section size as well as the tension steel area, considering the high material mechanical performance. And recently, we proposed that we should significantly reduce the cross-section size and use a higher reinforcing ratio than in typical concrete beam to utilize high compressive strength and resulting higher reinforcing ratio capacity in UHPC. So we can significantly reduce the cross-section size. So with a higher reinforcing ratio, we are not putting more steel rebar, we are just significantly reduce the cross-section size. So the reinforcing ratio will seem higher, but we are not putting more rebars than steel reinforced concrete. And then the question is, which design philosophy is most ideal for sustainable design? And third motivation is, as we mentioned, people has hypothesized that UHPC structure will show much higher corrosion resistance or life cycle than steel reinforced concrete structure, but no one has ever quantified or actually analyzed the lifespan of reinforced UHPC structure under corrosive environment. And also, we are wondering if reducing the fiber volume and it will reduce the cracking resistance, how it will affect the life cycle performance of UHPC structure. So to under these 4 research questions, we have 3 phases of research. The first phase is we are comparing reinforced UHPC beams with different philosophies and fiber volumes. We adopt nonlinear phenomenon analysis and cradle-to-gate carbon footprint analysis. In the second phase, we select the most ideal beam design philosophy and compare UHPC beams with different material composition. Basically, it's a replacement of cement by supplementary cementitious material. And in the third phase, we select most preferred UHPC beam designs with different fiber volume and do a corrosion analysis and compare to conventional concrete. So those are the 3 phases. And then, just briefly introduce the methodology. We have a 2-dimensional nonlinear analysis that has been validated by experimental design. And we use a cradle-to-gate life cycle assessment to analyze the initial carbon footprint of UHPC and concrete beams. And then we use multi-physics corrosion analysis to consider to do circles to consider the corrosion progress and the impact of the lifespan of our beams for both UHPC and concrete beams. And then let's briefly talk about the design test matrix for phase 1. So we have 1 concrete beam. We have 4 different UHPC beams. The first beam adopts the same cross-section size, much reduced reinforcing ratio. Second beam with a similar reinforcing ratio, but reduced cross-section size. Third beam with a much reduced cross-section size and a higher reinforcing ratio. So these 3 beams all have 2% fiber volume, and the last beam is similar to the third UHPC beam, but with a 1% fiber volume. And here we show the material properties of UHPC compared to concrete. So you can see that it has higher compressive strength, higher elastic modulus, higher compression ductility or compressive fracture energy, as well as high tensile strength and high tensile fracture energy, which is material behavior we previously discussed. And then since time is limited, let's just briefly review the results. So first, when we are looking at the initial designs, we want to make sure that the black line here is a concrete beam. So concrete beam is a black line. All the colorful lines are UHPC beams. So all the UHPC beams has a similar or higher stiffness at the initial stage than the concrete beam. So the stiffness control is satisfied. And when we are considering ductility, except the beam with low reinforcing ratio, which fell after crack localization, all the other UHPC beam designs show higher ductility than reinforced concrete beam, which is expected because they all fail by crashing or eventually fracture, and the high compressive ductility of UHPC allow a high structural ductility in the UHPC beams. And then when we are comparing the cradle to gate, carbon footprint, the first column is a concrete beam, and these columns are the UHPC beams. So we can see that if we can utilize the high reinforcing ratio and significantly reduce the UHPC beam cross-section size and therefore UHPC beam material usage, the UHPC beams can actually show a similar initial carbon footprint as concrete beam. So we are not actually increasing the carbon footprint of structure, and because we reduce the superstructure weight, we can further reduce the column size and foundation size, and I may further reduce the carbon footprint of the entire structure. So in conclusion, that this design with high reinforcing ratio and heavily reduced cross-section size is more preferred for reinforced UHPC beam design. And then we'll enter the second phase to think about the influence of material composition, especially replacing cement by supplementary cementitious material. So we have, in addition to the UHPC beams we've seen in the first phase, which is here, we introduce two green UHPC or GUHPC with lower cement. So in these two green UHPC beams, the cement content is replaced by fly ash and slag. So if we look at the material property, after replacing cement by fly ash and slag, we inevitably reduce the compressive strength and elastic modulus of the material, which has been observed by other papers with low cement UHPC as well. So typically, reducing cement content will reduce the compressive strength and elastic modulus of the material. Then we are designing, again, utilizing a high reinforcing ratio, we are designing the beams with similar stiffness and load capacity so we can more directly compare their carbon footprint. So again, we are showing that all the beams have similar stiffness, similar load capacity, but UHPC beams has higher deformation capacity. So surprisingly, we find out that although those green UHPC material may reduce the material level carbon footprint, but in order to reach a similar stiffness or load capacity, these beams need to have a larger cross-section size because of the lower material mechanical performance. So actually, the environmental impact is similar. So that proposed a challenge to the material engineers that when we are trying to replace cement with other materials, we probably want to find a way to not reduce the mechanical performance of the material. So we can actually reduce initial carbon footprint with those greener materials. So then we'll select these three beams for our corrosion analysis. So the concrete beam and two UHPC beams with two different fiber volumes. And then we see that under a very corrosive environment, so we select intentionally a very corrosive environment, and the traditional reinforced concrete beams will crack and lose load capacity due to steel corrosion after about 20-30 years on a very corrosive environment. But for both UHPC beams with 1% fiber volume, one here represents 1% fiber volume, and UHPC beam with 2% fiber volume, the high cracking resistance much extend the lifespan of the structure by providing high cracking resistance and slow down the corrosion process of our beam. So under aggressive environment, both UHPC beam with 1%, 2% fiber volume actually shows over 20 times longer corrosion resistance than the traditional steel reinforced concrete beam. So with that, I conclude our seminar today, and then I think I'm right at the 45 minutes point here. And thank you for your attention. And now I welcome any questions.